Greetings viewers, in this video we'll go through Cambridge A-Level Further Mathematics, Syllabus Code 9231, Component 3 which is Further Mechanics. This is variant 1 from the May June 2025 series. We'll go through question 5 and the previous questions are already uploaded to the playlist. So question 5 is giving you a lot of information again. We'll slowly read through it. Light elastic string, so we'll just model it as a spring and a natural length of 0.5 meters. So we'll just write this down. Natural length or unstretched length L naught is 0.5 meters. The modulus of elasticity, Young modulus, 14 newtons, and it's attached to a fixed point A on a smooth plane. Okay, so smooth plane means we'll ignore any friction, and the plane makes an angle alpha to the horizontal. So maybe I'll just sketch this out first. So this string is on the fixed point A and it makes an angle alpha to the horizontal, and tangent alpha is 7 over 24, so might as well label it now first. So using this we know also that this will be 25 using the Pythagoras theorem, right? So that's about the tangent, the angle thing. Particle P of mass 2 kg, alright, so the mass is 2 kg, is attached to the other end of the spring. The string lies along a line of the greatest slope of the plane. P is initially held on the plane above the level of A. Okay, so initially, just write initially here, it's on top of it where AP is 0.8 meters. So initially the particle is here on the string and it is 0.8 meters away. Alright, so it's stretched basically. Basically it's 0.3 meters stretched from its original length. And it is released from rest. And they want us to find the maximum velocity of P during the subsequent motion. So this initial, final, it will become, okay, it's released from rest, so definitely it will slide down the slope, and it's frictionless. So at some point, it will end up down here. And we want to find the maximum velocity point. Okay, so we're going to we have all the information that we have to find or to use the energy method. So the conservation of energy. So if you can recall, conservation of energy states that energy cannot be created or destroyed, just transferred. So the change of energy, the total change of energy in any system will be zero. So the initial energy will be equal to the final energy. Of course, in this case, we are not considering any wasted energy, any friction energy that's lost to heat or anything. So it's just a perfect system here. First of all, let's consider the initial scenario. Initially, what energy does it have? It will have the spring energy and it will have the potential energy. So again, we model the string as a spring. We assume that it does not break or anything. So, and also we will set the datum. I guess we'll just set the datum here, because at this point, we'll set this as the datum such that everything that we measure, what we call the gravitational potential energy, will be zero at this datum. Let's do the spring energy first. So the energy of spring at the initial point, we're going to use this formula, this one, lambda x squared over 2L, lambda x squared or x initial squared over 2L naught, and stretch length. Lambda in this case given us or E, which is the Young modulus, 14 multiplied the stretch length initially, that's 0.3, and divided by 2 unstretched length is 0.5, so we get 1.26 joules from this. Okay, the units or dimension is energy, so it's joules. Now we don't consider the potential energy or the gravitational potential energy here. As I said again, we set this as a datum, so we just measure the change of the height later on. Okay, so it's also initially at rest, so ek is 0 at rest, right? Then E gravitational initial is 0 because it's at datum. So these are the initial condition. Now we'll go for the final energy. So this one is a bit tough because at the final point where we want it at the maximum velocity, we're going to need to know a few things. At the maximum velocity, it will be in equilibrium because at that moment, that is when the string uh, does not exert any force, or it does exert the force, but it's balanced together. Or let's draw the free body diagram, right? At this point, when it's at its maximum speed, it will have its weight and it will have the tension. So at this point, at the fastest speed, it will be in equilibrium, so that there is no acceleration. Because after that point, where if it stretches any further, it will start to exert a larger tension compared to the weight. So that at that point, it will start to slow down already. Right. So we want the point exactly where the acceleration is zero, so that that point is right before it slows down and is at its maximum speed. Let's find that point first, or let's use the information that we have to get the point at its maximum speed. So we can try to resolve the forces here. Resolve this weight, gravitational weight force, like this, like that. Since the alpha is here, so our alpha will be here. Okay, using the some I forgot what's the theorem, but you should probably know this by now. So the alpha is there, and when at Vmax, the spring and the particle will be at equilibrium. Vmax, it will be at equilibrium. The sum of the forces in the y direction, it will be 0, and we take the y as this one, y. So t minus mg sine alpha, that is 0 at this instant, at this instant. Okay, we consider this instant, and t will be equals to 20 sine alpha. So m is, we written before, m is 2 kg, g we take as, again with g, reminder, we take as 10 meters per second squared, not 9.81. So please don't confuse with that. So 2 times 10 times sine alpha, which will be 7 over 25. That's 5.6 newtons. And how do we find the extension or the position from here? We're going to use this formula, the one relating Hooke's law. Okay, so we have 5.6 newtons, and we equate that to lambda x over L. So, and this one will be the x final, xf lah. Okay, xf, you can do the calculation, 5.6, this is L naught, 0.5 over 14, and we'll get 0.2 meters. Right, we know that the extension here is 0.2 meters, so we also can use this to find, well, we have the change of height, right? So initially it's 0.8 meters above, or like the slanted length is 0.8, and then it falls 0.5 meters, that it will be the unstretched length. Then it stretches again to 0.2 meters, and so the height, it will be all this added together, so it's 1.5 multiplied by sine of alpha, right? Because the alpha is here, this one is alpha, and we want to get the vertical, yeah, this vertical line here. And using this will be the opposite of the angle, so we use sine. We can directly substitute that because we have the values also. So delta H, 1.5 times 7 over 25, so 0.42 meters. Okay, the final energies, what we have the spring energy, E spring final. So that will be, again using the formula, lambda x f squared 2 L naught. And kinetic energy, we don't know what's the velocity, that's what we want to find. So we're just going to use the formula, half of mv v squared, v max squared. At this point, it will be v max. It will just be v squared after simplification. And we also have the change of the potential energy, or gravitational potential energy. So that will be just mg delta h. and since it's a negative change of height, so you get a negative value for this. Is 8.4 joules, negative 8.4 joules. So let's do the conservation of energy. So sum of initial energy will be the sum of the final energy. Initial energy, again, we only have this spring energy initially because it's at rest and it's at the datum. Final, we will have the spring energy 0. This is joules, right? This unit is wrong. Let me highlight for you. I label wrong this unit. This should be in joules. Yeah, 0.6 joules. Then we have the kinetic energy component, so it's just V squared. And we have a negative 8.4 joules here because of the change of height. I think it has an error not just here. Something I typed wrong in my calculator. This should also be, this entire thing is wrong. Don't know why. This should be 0.56 joules, not 0.6 meters. Not sure where they got that from. So this one also 0.56. And therefore, yeah, these two values are wrong because of that. V squared should be 9.1 and V is 3.02 meters per second. Yeah, so this is how we use the conservation of energy theorem to solve this type of question. Thanks for watching.